Hello everyone, this video is going to be an introduction to statistics and going through a few examples as well. So the first thing that we need to think about is a few things of terminology. So the sample space, which is denoted by this capital omega, is the set of all possible outcomes of an experiment. So it's everything that can happen. For example, if your experiment is rolling a dice, the sample space is all the numbers from 1 to 6. Then an outcome, which is denoted by, it looks like a W, but it's a lowercase omega. This is any element of the sample space. So back to the dice example, if you're rolling a dice, the number 4 could be an element. An event is a collection of outcomes. So this is any subset of the sample space. So back to our dice throwing example. So as I said, the sample space is 1 to 6. An event could be 3, and an outcome could be 3, and an event could be an even number, which will include the numbers 2, 4, and 6. And our overall goal in a lot of these questions is to find the probability of A, which is the event A. So we use Kolmogorov's axioms, which are very useful and lead to a lot of useful other things. So the first thing is the probability of any event has to be between 0 and 1. So this says that probability can never be negative and it can never be greater than 1. The next thing we know is that the probability of our whole sample space is 1. So if you're throwing a dice, the chance of throwing a 1, 2, 3, 4, 5, or 6 is 1. You have to throw at least one of those. And that's the second axiom. And the third one is that if you have events A1, A2 going on, and they're all pairwise disjoint. So pairwise disjoint means there's no overlap. So event AN and AM are equal to the empty set, the intersection of those two sets, when N is not equal to M. So different events have no intersection. Then this tells us that the union of all these events will be equal to the sum of the probability. The probability of the union of these events is equal to the sum of the probability of these events. Then the last thing to highlight is that a probability of 0 doesn't necessarily mean impossible, and a probability of 1 doesn't necessarily mean certain. The way I like to think about this is when you're throwing darts at a dartboard, the probability of hitting any exact spot is actually 0, because you'll never hit any exact spot. And another thing is if you flip a coin an infinite number of times, the probability of hitting at least one heads is 1. You'll definitely hit one, but it doesn't mean it's certain. So the terminology we use is we say if it has a probability of 1, we say almost surely. So that's just something to keep in mind. From the Kolmogorov axioms, we get a number of useful results. So we're just going to say the sample space is a set, and P be a probability measure, and A and B, which are subsets, that's the symbol for subsets of the sample space, be events. So the first thing we're going to use is that the probability of the empty set is equal to 0. It's quite obvious, I would say. The second one is that for any pairwise disjoint events, so before we had an infinite number, now we have a finite number where it ends at n, which are a subset of the sample space. The probability of the union of all these events is equal to the sum of the probability of these events. So it's very similar to number 3, except here we have an infinite number, it just goes on forever, and here we have a finite number. The way I like to think about this one is by using a picture. So this square will represent the whole sample space, and I've split it up into 6 different events: A1, A2, A3, A4, A5, A6. So if we want to find the union of, let's say, A1, A2, and A3, A1, A2, and A3, we can to find the union of them, we can just add them up. So we can say this area plus this area plus this area. So that's kind of how you would apply this. And I'll give you another example. So let's say you're throwing a dice and you have event 1, which is the number is either 1 or 2, and you have event 2, which is the number is either 3 or 4. As you can see, A1 and A2 are pairwise disjoint. There's no overlap. There's no element that's common between these two sets. So we have the probability of A1 and A2 is going to be 4 over 6, and the probability of A1 plus A2 is 2 over 6 plus 2 over 6, which is 4 over 6. So as you can see, that and that are the same. And then the third useful result is that the probability of, so when you have this little C above it, that means the complement. So the probability of A complement, which is not A, is 1 minus the probability of A. So we can see it using this picture. So A complement will be everything except for A in the sample space. So I'll highlight it. So A complement is going to be all of that, okay? And that's going to be 1 minus the probability of A. And the probability of A, green, is going to be this. So as we know that the whole sample space is 1. So if we take the whole sample space 1 minus this, we can clearly see that it's going to give us this yellow region. Number 4. So it says that if A is a subset of B, then the probability of A is less than or equal to the probability of B. And the probability of B set subtract A, so you're subtracting the set A from set B, is equal to the probability of B intersection A complement, which is equal to probability of B minus A. So this one's a little bit tricky to think about, so I drew a picture. So here we can see I drew all the probabilities. I drew a few different probabilities from A to E, and we can clearly see that A is a subset of B, which is this whole block including A, so that's the whole of B. So we can see that A is a subset of B, and then we can also see the probability of A, which is the size of A, is less than the size of B here, but it could also be equal if A and B are equal. So now if we take B and we subtract A, we'll just get this region, which I'll highlight in yellow. So we'll just get this region like this without A. So basically we'll get the whole of B without A, like that, without that. And we can clearly see that this is equal to, so now if we have a look at the probability of B, I'll highlight the probability of B in yellow. So the probability of B includes A, so that's everything. And the probability of A complement, which is not A, so everything except for A. So I'll highlight that in green. So everything except for A, so it's all of this little bit. So it's basically like all of that. So, and then we're looking for the intersection. So when you look for intersection, you see where the two highlighted sections overlap. So we can see that they don't overlap here because there's no yellow, and they don't overlap here because there's no green. It's only here without this bit. So we can see that this is saying the same as this. And then the probability of B minus the probability of A is exactly the same thing. So it's the probability of B, which is this whole chunk. It's basically like we've cut out a little circle of A using a cookie cutter. So we basically, B without A is the same as that, is the same as that. So, and number 5, which is also very useful, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So the easiest way to look at this is with a picture. So let's look at the probability of A. So let's highlight that. So the probability of A is going to be this whole circle here. So that's going to be A. And the probability of B is going to be this whole circle here. Okay. And then the probability of A or B is them both combined. But as you can see, when you highlighted it, we highlighted this middle region twice. So what we have to do is we have to subtract the probability of A and B, which is this middle region, right here. So we have to subtract that because we added it twice, basically. Cool. There's 2 more useful results that you often use in statistics. So this says that if you have A1, which is a subset of A2, which is a subset of A3, A4, going on, and they're a sequence of increasing events, then the probability of the union of all these events from n1 to infinity of AN is equal to the limit as n tends to infinity of the probability of AN. So I thought this was a little bit tricky to think about, so this is an example. So let's say we toss a coin, and AN is the event that at least one head occurs in the first n tosses. So A1 will be a head on the first toss, A2 will be a head on the first or second toss, A3 will be a head on the first or second or third toss, going on. So we can clearly see that A1 is a subset of A2, which is a subset of A3 going forward. And the intersection from n1 to infinity of AN is the event that at least one head occurs eventually. So if you had like A100, that would be at least one head occurs in one of the 100 tosses. And infinity basically means that if we keep tossing forever, eventually a head will occur. So the probability of AN, so we're going to use one of the rules from earlier. The probability of, so we're using the rule that the probability of A complement is equal to 1 minus the probability of A from here. 1 minus the probability of A, but now what I did here is I just swapped them, so I just moved that one to that side and that one to that side, so it's exactly the same. And we know that the probability of A complement is the probability that no head occurs. So the probability that no heads occur on each toss is a half, because each toss can either be a head or a tail, so it's a half to the power of n. So now if we take the limit as this tends to infinity, I'll just put it here. I'm just going to put the n here, so 1 to the power of n just gives you 1, and 2 to the power of n. And you know that as n gets really big, this number is going to get really big, and 1 over a really big number, like 1 over something to infinity, is going to be 0. So this becomes 0, so then it just becomes 1. That's how we evaluate the limit, and this matches our intuition that if we tossed an infinite number of times, at least one head's going to occur. Okay, so this is the kind of opposite of that. So that now you have A1, and A2 is a subset of A1, and then you'll have A3, A4 going on like that, and a sequence of decreasing events. So now, before you had the union, now you have the probability of intersection from n1 to infinity of an is the limit as n tends to infinity of the probability of an. So let's do another similar example. So let's say we toss a coin, and an is the chance of no heads, is when no heads appear in n tosses. So a1 is you get tails on toss 1. So no heads just means you get tails on basically all your tosses. So a2 is you get tails on toss 1 and 2, a3 is you get tails on toss 1, 2, and 3, and like a100 will be we get 100 tails in a row, basically. And we can clearly see that as you go on, they're each a subset of like a1, a2 is a subset of a1, and a3 is a subset of a2. So they're decreasing events. So the intersection from n1 to infinity is the event that all the tosses are tails forever, which our intuition tells us probably 0. So let's have a look. So the probability of an is a half to the power of n. As we saw earlier, the probability of a tail on each one is a half to the power of n. You could do this doing tree diagrams, but it should be quite obvious. So we're going to take the limit as n tends to infinity. Again, 1 to the power of n is just 1, and 2 to the power of n is 2 to the power of n. And now we take the limit as n tends to infinity. So this number gets really big, the n gets really big, which means 2 to the power of n gets really big. So it becomes kind of close to infinity. And 1 over infinity, and you can't really use infinity as a number, but 1 over infinity is about 0. So that matches our intuition. Okay, so I hope that was useful. I hope you enjoyed this video, and I'll see you next time.